Okay, so it's time to continue. Our next speaker is Damien from McGill, and he will tell us about spectral triples on the Berkovich line. It's all yours. Take it away. À vous, monsieur.
Thank you. Thank you for the kind introduction. Thank you for the organizer for having me here. It's a great pleasure for me to talk. So this is a joint work with Masoud Khalkhali. It's a project we started in early September, and this is still work in progress. So I'm going to present the general background and some of the ideas that we got since then. So let's start with the motivation of the problem. So if you have a rational map acting on the complex plane, you can study its dynamic for its own right. But it turns out that there is a relation between the dynamics of the map and the arithmetic property of the space and some geometric property. And so this goes back to the work of Sullivan. There is a dictionary between so the points on an abelian varieties and some periodic points of the rational map. Another thing to notice is that it's a philosophy, general philosophy in arithmetic, is that before studying something in the complex plane or on rational maps, one should study them on periodic numbers. Okay? So one would like to extend this picture from arithmetic geometry to dynamics from the complex case to the periodic case. Okay, so one has to extend this to non-Archimedean fields. So what is a non-Archimedean field? Well, you start with a non-Archimedean absolute value, and the important point here is that you replace the triangular inequality by this ultrametric inequality, and then you take the completion, you get yourself a non-Archimedean fields. So one would like, usually to work in the projective line. So you could try to construct P1 of K. In all generality, what you might get is something that is totally disconnected and not locally compact. Okay? And what this means is that the topology that you're looking at might not be the right one. In the 90s, Berkovich constructed a much nicer object, which is now called the Berkovich projective line, and has, as I said, much nicer properties. So let me now introduce this object. So it starts with the multiplicative semi-norms on your space of polynomials. So the multiplicative semi-norms are semi-norms that are extending your absolute values. And you take, if you have a norm ring, if you consider, well, the analytic spectrum, or something that is called the Berkovich spectrum, is a set of all non-zero multiplicative semi-norms, and you equip it with a topology such that these are continuous. And so if you do so, well, you get the Berkovich affine line, which is a set of all multiplication semi-norms. You can compactify this to get the projective line. And it turns out that P1K sits in this projective line. And if you remove it, you get the Berkovich hyperbolic line. Okay, so all of these spaces are equipped with the Gelfand topology, and they have much nicer properties. Well, the first one is that, well, you can represent them. Okay? They are represented as trees, actually as rooted trees, inverse limit of rooted trees. And you have a classifications of the points on these trees. Okay? So the type 1 points are the points that are on the boundary and at the limit. The type 2 points are the branching points. So in all generality, the number of branching could be uncountable. If you work on CP, then you have finitely many of them. The type 3 points are points where you have no branching, and the type 4 points are points that ends before reaching infinity. Okay. It has other nice properties. Well, first, it's compact, path connected, Hausdorff. It has a metric. It is, as I said, and this is going to be very important, it is homeomorphic to the inverse limit of finite rooted trees. And it's an hyperbolic space in the sense of Gromov. You can define a Boltzmann function on it, which heuristically measures a large-scale evolution of the geodesic on the trees. And last but not least, you have an arithmetic on this. So what do I mean by this? Well, you have a lot of work done in this direction, starting by Favre, Rivera, Letellier, Baker, Rumeli, Autissier, Chamberloir, and Tuillier, which gives you something called a canonical measure. And this canonical measure, to be brief, encapsulates the arithmetic information on this space. So it's an equilibrium measure that you can construct on this space. And they are conformal, meaning that if you take a rational map, you can associate a measure to it. And if you pull it back, well, you recover your measure times a constant d, which is the degree of your rational map. The measure of the exceptional set of your rational points is also 0 under this probability measure. Okay? And so this result is the starting point of arithmetic in the non-Archimedean case. And the whole idea of our work would well, maybe I should say a point about also how to find, how Baker and Wumeley found this measure is through potential theory. So because this space, this Berkovich space enjoys nice properties, you can define potential theory on it. And one of the main objects of potential theory is the Laplacian. So you need to define harmonic function, subharmonic function. So you need a Laplacian. In a sense, you need some sort of differential calculus on your space. And the idea would now to, well, if this is possible to be done using potential theory, we're not trying to use spectral triples and see if the non-commutativity in the picture will bring us a similar result or other type of results. Okay, so now let's see how we can construct spectral triples on this Berkovich line. So you can start from simply from the fact that the Berkovich line is the inverse limit of finite rooted trees, and you can construct a spectral triple on each of these trees. This is a usual construction in spectral triples. You take A to be, well, here we'll, for now we are on the commutative case, so you take the Lipschitz continuous function on the graph, you take your Dirac operator to be defined usually by the Pauli matrix, and the eigenvalues of the Dirac operator will be related to the distance between the vertices on your graph. And because you have an inverse limit, well, you can define a morphism of spectral triples between two graphs, and then you can take the limit of a spectral triple, and you have yourself, you're just constructing a spectral triple on this Berkovich space as an inductive limit. So it's a commutative one. You can do many things on it. Well, the first thing that you can notice is that, well, it's usual, but you can recover the metric properties of your space by this studying this triple. You can define a measure on your space using the usual zeta function. You can construct a Dirichlet, what is called a Dirichlet forms, which is related to self-adjoint operator that you can identify to be your Laplacian on your space. It's related to a Markovian semigroup and so on. This is interesting. However, you might not get the canonical measure this way. In fact, if you want to get interesting arithmetic properties of your space, what you need to do is you need to change the algebra you're working on. You need to work on a non-commutative one. And how to see that? Well, okay, so you have rational maps acting on this Berkovich space. The set of automorphism of the Berkovich line is given by PGL2. If you take a discrete subgroup of PGL2, well, you can construct a semi-direct product between the continuous function and this subgroup with the usual contravariant representation. And in that case, you have an interesting one-parameter automorphism given by this. And this automorphism has a unique KMS states given at inverse temperature beta equals to some number delta, which is related to the dimension of your set. And actually, this KMS states is known to be the Patterson-Sullivan measure. So it's a measure that is related to the dynamical properties of the action of this element of your group, and it's a conformal measure. Okay. You have an Hamiltonian associated to this state, and from this you can build one cocycle from which, well, such that the square of this cocycle give you back the distance, and you can define a Dirac operator associated to this one cocycle, such as the square. Well, from the square you recover the Hamiltonian. Okay, so this is restricted to the case of element of a group, but in fact this is not what we want. Actually, it's just partially what we want. What we would like to be able to describe is a dynamic for arbitrary rational maps, not just maps that are belonging to this subgroup. So another way of thinking about this, but only from here, I mean, already from here, you see that just by switching the algebra, you get a much nicer properties. But another way of attacking the problem is to look at something called iterated function systems. Okay, so you fix a rational map, and you fix a set that is invariant under this rational map, and you define the graph of this map. You can construct something called a C-star correspondence. So you have a C-star algebra, which is the usual continuous function on your set, and you define a Wright-Hilbert A module from the continuous function on the graph. Okay, with the inner product given by this sum here, where the term right there is related to the multiplicity of the rational map. Okay, and this is very important. In the case of, in the complex case, this has been done by Watatani and Kajiwara, and since then it's called the Watatani-Kajiwara algebra. So it's a particular case of algebra, called the Kunz-Pimsner algebra, applied to this specific case. So how to construct this algebra? So you construct the Fock space from this Wright-Hilbert module. You have a top-list representation, and the Kunz-Pimsner algebra is just this algebra modding out the compact operator, and you get this algebra, and you have a gauge action, okay, given by multiplication by this complex number. And this has a unique KMS state at inverse temperature given by beta equals to the logarithm of the degree of your rational map. Okay, and it turns out that this KMS states is exactly the probability measure that you get from potential theory, but now looking it completely from a non-commutative perspective. Okay? Now the whole goal from here is to construct a Dirac operator and then a spectral triple associated to this KMS state. Okay? So there have been work done in this direction. And actually, one can do that, and you get something called an infinite dimensional spectral triple, which gives you back this KMS state. Okay. So if I want to summarize everything, so we have three different construction, if you want. We have the commutative one, which is the classical construction on finite graphs, that gives you, I mean, even if it's in the commutative case, it gives you already interesting properties. For instance, you can define these Dirichlet forms and something that you can call the Laplacian. But if you want to get a dynamics property, then you have to move on to the non-commutative case. So if you fix a discrete subgroup, then you have this Patterson-Sullivan measure. And if you move on to this Kajiwara-Watatani algebra, then you can recover the probability measure from that Baker and his collaborator has constructed. So there are many remaining questions to address here. Well, the first one is, can this work be related to something called non-commutative potential theory? So there have been work done in that direction in the literature. So it would be interesting to see if there is any connection. Another thing is, if we get infinite dimensional spectral triples, another question that we may address is the summability of these spectral triples. And well, third but not least is, well, can we really get arithmetic information just by studying these spectral triples? And this is all I had to say, so thank you for your attention.
Merci beaucoup.
Merci.